xd of omega just becomes this scaled, stretched version of xa of omega. And then outside the range minus pi to pi, I get this repeating. So in the expression where we have x of d of omega is 1 over t, the sum of xa of omega over t plus 2 pi k over t, this copy, the copy that resides for omega between minus pi and pi, this copy is the k equals 0 term in this sum. This copy over here that sits at 2 pi, this is the k equals 1 term. This copy at minus 2 pi is the k equals minus 1 term. Now there's an infinite number of these terms, but notice that they don't overlap. So really all of the information that I need is sitting right here between minus pi and pi. So in the range, magnitude of omega less than or equal to pi, this relation, if these don't overlap, so if 1 over t is greater than b over pi, then in the range minus pi to pi, x of d of omega is just 1 over t, xa of omega over t. This is really just a statement of the Nyquist criterion. We need 1 over t to be bigger than the spectral width of the signal. And if that happens, then we don't get these copies, the k equal 1 copy, leaking in and overlapping the k equals 0 copy in this expression. Now, what happens if this condition doesn't hold? If this condition doesn't hold, then, in other words, if x of a of omega is not 0 for the magnitude of omega greater than or equal to pi over t, then what happens is something called, we have aliasing, where some of the frequencies in this copy leak into the range from minus pi to pi, and they masquerade or alias as lower frequencies. So let's take a look at an example like that. Let's let t equal 5/3 pi over b. So then 1 over t is equal to 3/5 b over pi. And it's not greater than b over pi, so we don't satisfy this condition. We're not sampling fast enough. Then what happens? Well, starting with this same canonical spectrum, something that's band limited from minus b to b and has height 1, let's draw the k equals 0, k equals 1, and so forth terms. I'll draw it over here. So the k equals 0 term, let me give myself thirds. That's pi over 3, 2 pi over 3, pi, and 4 pi over 3, 5 pi over 3, 6 pi over 3, which is 2 pi. and then 7, 8, 9 pi over 3, which is 3 pi. This is omega. And that's minus pi over 3, minus 2 pi over 3, minus pi, minus 4 pi over 3, minus 5 pi over 3, minus 2 pi, minus 6, 7, or 7, 8, and minus 9 pi over 3. Okay, so since t is 5/3 b over pi, then b times t must be b times 5/3 pi over b. So b times t becomes 5 pi over 3. So 1, 2, 3, 4, 5 pi over 3. So the k equals 0 copy gets scaled by 1 over t, and stretches from 0 to 5 pi over 3. This is 5 pi over 3, and that's minus 5 pi over 3. This is the k equals 0 copy in this expression. K equals 0. Now, where does the k equals 1 term go? K equals 1 term always is going to be centered at 2 pi, but now it's going to reach back from 2 pi. So this centered at 0, I go from 0 up to plus 2 to plus 5 pi over 3 and to minus 5 pi over 3. Centered at 2 pi, I have to go forward 5 pi over 3 and backwards 1, 2, 3, 4, 5 pi over 3. So and then 1, 2, 3, 4, 5 pi over 3 forwards. This is the k equals 1 term. The k equals minus term starts at minus 2 pi over 3 and extends forward 1, 2, 3, 4, 5 pi over 3. And goes backward 1, 2, 3, 4, 5 pi over 3. This is the k equals minus 1 term. So what you notice is we no longer have the case where the two copies don't interfere, but instead we actually have the case where these two copies are right on top of each other. So in this range here, after sampling, we actually have the superposition of these two spectral components, and because these are nice simple triangles, actually these two add up to be this nice flat curve going across. So the net result is a spectrum that looks like this. Between 0 and pi over 3, the spectrum still has this nice triangular shape, height 1 over t, but then it's flat. We've lost all of the spectral information, or we've combined spectral information from these low frequencies and these high negative frequencies and so forth.